Hi, my name is Alfred Beshara, and today I'll be discussing the effects that calculus has had on a study called marginal cost and revenue, which is a prime branch of economics. In terms of structure, I've split this presentation into three sections. In the first, I'll be explaining and describing the field of economics, then shall delve deeper into marginal cost and revenue. The second part will be to outline the problem that calculus has solved within the broader sense of economics. Then I shall examine my selected topic, and in the final section I will present and solve three calculus-based problems associated with marginal cost and revenue. I hope you enjoy my presentation, and please do not hesitate to pause at any time to digest information. Let's start by explaining what the study of economics entails. Economics has been classically defined as the study of the use of scarce resources which have alternative uses. This basically means that since businesses need resources for the production of certain goods, and because these resources are finite, for example time and money, then what economists do is analyze the choices that a particular organization ought to do in order to maximize the production line and thus profits. All studies pertaining to economics come under one of two categories, positive or normative. Simply put, positive economics answers questions such as, why do people buy goods? Whereas normative economics answers things like, should people buy goods? In conjunction with positive and normative, economics may also be divided into macro and micro. Macroeconomics addresses the large-scale factors such as interest rates, rate of growth, etc., whereas microeconomics is concerned with single factors such as individual decisions and the economic implications that follow. Now that we've explored what economics is in a broad sense, let's examine marginal cost and revenue. Marginal cost and revenue is a branch of microeconomics which deals with the maximization of a particular item's cost as well as the maximization of the revenue that is generated. For the sake of clarity and depth of analysis, I'll first explain this concept theoretically, then shall illustrate it practically through the use of an example. Now economically, this theory states that a business should only continue to manufacture products as long as their marginal revenue is equal to the marginal cost. Marginal cost and revenue may be defined as the additional expense or profit that is made by selling one more unit of a product, respectively. Examining Table 1, two things may be inferred. Firstly, we see that the revenue, the price at which a product is sold, is at a constant rate. Secondly, the marginal cost of a product varies depending on the quantity purchased. With both of these variables in mind, any business therefore determines the amount of quantity that ought to be bought based on the amount of profit that is generated, which in this case would be quantities 60 and 70, as they will both yield $5 each. One thing to note is that in this table also holds true to the fact that if marginal cost and revenue are equal, then we will inevitably maximize profit, as if we were to look at quantity 70, we would see that although its cost and revenue are equal to $0.6, it still has the highest profit out of the entire table. Since we have had a look at marginal cost theoretically, I would like to now illustrate it through a practical example. An orange orchard, and you sold every orange for $1. After calculating the marginal cost and revenue of your business, which in this case would be the cost of equipment and employees' wages, the results showed that the oranges at the bottom of the tree are the cheapest to collect at 60 cents due to the lack of hiring equipment and the time taken by the collectors. The results also showed that if you were to harvest from the middle of the tree, it would be at a higher marginal cost of 80 cents because the time spent attending to the equipment as well as their costs. And the final calculation showed that if you were to harvest from the top of the tree, then your marginal cost would be equal to $1.20 due to hiring a large ladder as well as the time spent operating on it. Since, however, every orange is sold at $1 and the marginal cost is $1.20, then you would be losing 20 cents on every orange sold, so economically you would not want to collect from the top of the tree. As a business owner, however, you would want to collect from the bottom of the tree, as you'd be making 40 cents on every orange, as well as from the middle of the tree, as you'd be making 20 cents. And this is essentially what marginal cost and revenue consists of. It is the analytical calculation of the entire production cost of products, as well as the assessment of financial decisions. Now that we have had a look at marginal cost and revenue theoretically and practically, the focus of this presentation will be shifted to the problem that calculus has solved in economics. Even before examining in depth the complications that were faced before the arrival of calculus, any economist must admit that this study is so ingrained within the broader sense of economics. It is, as prominent American journalist Henry Hazlitt pointed out, the measurement by which economic information is analyzed. Based off of the words of Hazlitt, we may safely deduce that the problem economists face was that they were incapable of analyzing economic information and therefore unable to suggest how to efficiently use resources, which, as mentioned before, is the single most important purpose of economics. So essentially the entire study is predicated on calculus. With that being said, one can assert that calculus is almost like the stitching that keeps economics in place. A prime example of the importance of calculus in economics is the supply and demand curve. Even people such as myself, who haven't merely begun to fathom the full entailments of economics, have heard of the supply and demand curve. It is one of the central devices in the analytical evaluation that all businesses need in order to set functional prices for their products. Founded on the example of the supply and demand curve, we may even say that positive and normative economics is the result of calculus. The problem that has therefore been solved in the broader sense of economics is that it has established the foundation of the entire field. But if we were to further examine economics before calculus, we would see that things such as marginal cost and revenue were not yet invented. If we were to simply analyze the name of this field, we would see that the word marginal in the economic sense actually represents the change in one unit, or in other words, the derivative of either the cost or revenue for a particular product. If we were to next examine the word cost, we would see that it is calculated through calculus. Likewise, if we were to examine the word revenue, we would also see the derivative notation. Calculus is therefore not only at the core of this study as seen through the definition and formulas of each section, but it was due to calculus that this study was created. Okay, since we have inspected the problem calculus has solved for the study of economics, let's now have a look at 3 questions that may be solved through the use of calculus. The first problem that I'll be addressing is, given the production function is Q and the constant is L plus K equals 20, find the quantities of labor and capital so that the output of the quantity of goods may be maximized. Now before I go through the procedure, I think that it is important to note that this question involves partial differentiation. Now partial differentiation is a major field in both economics and calculus. As seen in this question, oftentimes economists wish to demonstrate how much money and production, for example, is needed in order to gain a certain amount of profit. This, however, is very difficult because oftentimes they cannot simply differentiate functions, as there are 2 different variables multiplied by each other, as seen even in this case. That's why they derive the function in terms of one variable and derive the same function in terms of another, which is essentially what partial differentiation is. And that is what we need to do in this case. So firstly, we must determine the first derivative of the production function in terms of L and K, which are the variables that we spoke about. So for this section, we must remember our differentiation power rule, which is, when we have an exponential function, we multiply the number in front of the subject, x, in this case L and K, by the exponent, or the number that our subject is raised to, and take 1 away from the exponent afterwards. When we, however, do so for our function Q, in terms of L, we get 2k minus 14L, and in terms of the capital function, we get 2L minus 10k. It is also crucial to note that you do not differentiate a certain variable in a function if that variable does not contain the constant that you are differentiating in terms. What this means is, if we were to take the labor function as an example, because we are differentiating in terms of L, the variable 5k raised to the power of 2 would become 0 because it does not contain the constant L in it. Likewise, in the capital function, the variable 7L to the power of 2 would become 0. Step has multiple parts associated to it. Firstly, using the rule seen on screen, we solve for our variable L in terms of K. Secondly, we substitute the findings into the constraint and find the value of K. And finally, we find the value of L using K. So part A of this step is to simply substitute the derivative that we found in the last step into the partial differentiation rule. When we do so, we end up with 2k minus 14L equaling 2L minus 10k. Now all that we have to do is clean this equation up using simple algebra. Firstly, we move the negative 14L to the other side by adding positive 14L to both sides. Then we move negative 10k to the other side by adding positive 10k to both sides. Then we are simply left with 12k equals 16L. Now at this point we could either solve in terms of k or L. I have chosen to do so in terms of L, but if you prefer to solve in terms of k, that would also be fine. Just keep in mind that if you do so, further steps may be contrary to mine. So all that we have to do here is divide both sides by 16, then we'll end up with L equals 3/4 K. Now that we've gotten up to this stage, we must substitute the 3/4 K into the constraint for the L variable, and we'll end up with K plus 3/4 K equals 20. Again, using our knowledge of algebra, we'll know that 1K plus 3/4 K equals 7 on 4K. So that's what we need to divide both sides by, which will leave us with K equals 80 divided by 7. Now that we've got the K value, we need to find our L. Again, using the constraint that was provided, if we do so, we'll end up with 80 on 7 for the K constant plus L to give us 20. So we just minus 80 on 7 to give us the L, equaling 60 on 7. Now step 3 is to determine whether the values that we have found for L and K are maximums or minimums through the second derivative test. Now after we derive the first derivative and find that the values are less than 1, we will know we have found the maximum point. Whereas if we derive the function and the answer is greater than 0, we will know that we have found the minimum point, as seen on screen. So first let's take the labor function and derive the first derivative once more. Again, remembering our power rule, and that if a certain variable does not have that which we are differentiating terms, then it will simply become 0. So after we differentiate our labor function, we get negative 14. Second, let's take the capital function and derive that again, and we get negative 10. Therefore, we have proven that both of our functions are maximums through the second derivative test. The next and final step is to determine what our maximum output of the number of goods will be by substituting 60 on 7 for L and 80 on 7 for K in our original equation. After we do that, we must multiply it out, remembering our order of operation, and we get 6,800 on 7. Therefore, approximately 871 quantities of goods are the maximized number based on our labor and capital variables. Now let's examine another question. The second question that I'll be addressing is, given that the cost per day for a poker chip company is given by the following equation, C of x, what is the marginal cost when x equals 2? Now before I begin with this procedure, I think it is important to note that to answer this question, we must understand 3 differentiation rules. The first is the derivative of function e. As seen on screen, we derive e by taking the derivative of the exponent and bringing that down. The second is the product rule. Now the product rule, as seen, is a differentiation rule that is used when we have 2 constants that contain the same variable, x in this case. And the final rule that we should be mindful of is the quotient rule. Now the quotient rule is used when we have 2 constants that may not necessarily have the same variable, as seen in our case, but that one contains a variable and is divided by another. Anyway, in order to answer this question, we must determine the first derivative of the cost function c of x. Now we do so, as mentioned before, by remembering our rules. Through all 3 rules we get c of x, as seen on screen. The next step is to merely clean up through the use of algebra. We know that anything multiplied by 0 becomes 0. We can also multiply things out, keeping in mind our order. And after we do so, we would want to expand the brackets, divide by 25 and 5, then we would be left with 2x e to the power of x to the power of 2 plus 15.606 x to the power of 2. Now step 2 for part A is substitute our marginal cost value, being in this case 2, into the first derivative of the cost function, which we just found. When we do that, we end up with 2 times 2 times e to the power of 2 to the power of 2 plus 15.606 times 2 to the power of 2. Now we just simplify and plug this equation into the calculator, and we end up with approximately 281. Therefore, the marginal cost when x equals 2 is $281. Now let's examine the final question, which involves integration. The third question that I'll be addressing is, after the collapse of the market for a single day, a small business thought that they ought to examine how much money they lost per unit sold. As illustrated on the right, calculate the amount of loss, given that we have f of x, g of x, and the coordinate for a is 1.390. Now before going through the process, I would like to indicate that this question uses integration, specifically the area between 2 curves. Finding the area under a curve and between two curves is a widely used technique in economics to find the area of loss that a company has suffered. The number that is then developed during this process then goes on to indicate certain things about the business's cost and demand. For the sake of time, however, I will not go through what the number can mean, but just keep that in mind. Anyway, the first thing that we must do in order to solve this problem is to integrate the first curve, which in this case would be f of x, between the selected points in question, being pi and 0. This, as seen on screen, will give us the entire area under the curve. So for this step we must remember our integration rule, which is, as seen on screen, add 1 to the exponent and divide the entire expression by n plus 1, then add a plus c, which stands for the constant. This simply means that our function is not entirely complete. In this case, however, we must differentiate a trig function, so the easiest way to do so is just create a table as I did. Okay, now through the help of both the table and integration rule, we may integrate f of x. And the way to find the definite integral is by substituting the higher x value, which in this case is pi, and then subtracting that from the integral of the lower x value, which in this case is 0. And so the way to now simplify this equation is to use what is known as a unit circle. A unit circle, as seen on the right, allows us to find the exact value for cosine and sine. Something that is important to note is that when looking at the unit circle, that the values on the outside are cosine and the values on the inside are sine. Now in this case we want to find the cosine of pi, which is just -1, and cosine of 0, which is +1. Now we can substitute those values in. Through the use of simple algebra we can tidy this equation up, and because we have a positive constant and a negative one, they may simply cancel each other out. We are therefore left with 2 root 2 plus pi squared on 2. Now the next step is to integrate the second curve, which in this case would be g of x, between the selected points in question, in this case being pi, and the coordinates for a, 1.39. As seen on screen, this will give us the area under g of x. Anyway, for this step we'll do exactly the same as the last, but in this time, rather than integrate sine, we'll need to integrate negative sine, and if we have a look at table 2, that would mean that it's positive cosine. Now all we have to do is substitute our points for pi and 1.39 into the equation as seen on screen. And because we know that cosine of pi is merely -1, we can also substitute that in. Now we can just simplify it by first expanding and collecting the like terms. After reaching this point, however, we should not simplify this equation anymore as we would risk having to round up too many times and left with an inadequate approximation. Now the third and final step is to subtract the second result, the area under g of x, from the first result, the area under f of x, so that we find the loss, or the area between f of x and g of x. It is important to note that although the curve goes beneath the x-axis, we do not calculate for it, as it is a negative loss, which is simply a profit. And because the question merely wants the loss, we exclude that from our calculation. Anyway, to solve for this part of the question, all we have to do is substitute our f of x and g of x into the equation provided. Then we simply use algebra by first expanding the brackets and simplifying. Now all that we have to do is plug this equation into our calculator, remembering that we are dealing with radians as we cannot find an exact value for cosine 1.39. Thus we find that the small business had a loss of approximately $5.5 during the collapse of the market. This concludes my presentation on the importance of calculus and the study of economics. I hope it has been educational and has provided you with an insight on just how fundamental calculus is in the field of marginal cost and revenue. Thank you.